everybody. This is the small video I made to help you with the homework assignment questions that I ask you to do for electric fields and forces. So the first question in the multiple choice, these are the questions starting on page 73 of your workbook. This is the definition of electric field strength. And when you look at the options, we see that the explanation in B is the best answer. It says the force per unit charge, positive charge on a small test charge placed at that point. Since E is F divided by Q, it's important that we say the force per unit positive charge, because when the charge is positive, field and force are in the same direction. So that is the best definition among these options. We skip number 2 for now. A test charge is a point charge which has no effect on the electric field in which it is placed. So we only use a small positive test charge to test what might be the direction of the electric field. So let's say we put a positive test charge here and we see that it experiences a force in that direction. We conclude that the electric field in that region must be in that direction as well. But in doing that, we don't consider what this positive charge adds to the field. That's why we call it a test charge. Number 4 is about the idea that we discussed before, where there are two charges in the given space. They are fixed in their positions and we're looking for an equilibrium position. Remember, if the two charges are oppositely signed, we have to choose the region outside their middle space because that's where their fields will be in opposite directions. And we need to give the weaker one the distance advantage. We need to choose the point closer to the weaker charge, which is point D in this case. To explain that better, I can show you what would happen at point D. So at point D, it's close to the 2 coulomb charge. We put a positive test charge here, and look what it is impacted by the other two. So +2 plus charge, this would repel. -7 plus charge, this one would attract, but it is bigger charge at a further distance. So the magnitude of its field would be equal and opposite, can be equal and opposite. However, if at point A, the field of the -7 charge, if you put a positive test charge here, the -7 would attract very strong at a close distance, but the 2 microcoulomb is further away and weaker. So even though it will repel, its field would be much weaker, so this cannot be in equilibrium. Moving on to number 5, this is more common sense and knowing what is like positive charge, negative charge, and the fields. We have a positive charge here, and another positive charge here, and one over there. So the one at X and Y are equally distant from P, and they're both positive. So their fields would be C due to this one and due to that one A, so they would cancel. And the field of this one at the center of the corner here would be again further away, B. So since these two cancel, it leaves B as our resultant field. Number 6 has a spherical conductor. So if we have a spherical conductor of radius r, we learned that inside the spherical conductor, any conductor, electric field is 0, which is why until r from the center we must have 0 field, and then maximum at the center and decreasing as you move along, which is what we learned. And then number 7, now we're looking for acceleration. Where did we learn about acceleration? In mechanics we learned that it's the rate of change of velocity, but we also know F equals ma. Now this, guys, will apply in everything and anything and everything that we learn. This is a general definition of any force impacting any mass, giving it the acceleration. So we're going to put this in context in no matter what we learn. Right now we're doing electricity. So which force is the force in context? Electrical force. How is electric force related to electric field strength? We know that F is equal to E times Q because this is how it appears in the data booklet, right? So you'll find this in the data booklet for electricity. So the electric force is the electric field strength, the capital E, times the charge that's placed. In our case, it's an electron placed in that field, and the electron charge is symbolized by E. So let's rewrite this equation by saying E instead of Q. And now we can find an expression for acceleration by dividing both sides by mass, and we get that. Now, to explain further, this is electric field strength, this is elementary charge divided by mass. Number 8 is another common sense question. There are 3-point charges, an equilateral triangle, and point P is the center of the equilateral triangle. In which case would the total field at P be 0? Answer must be A, because there are 3 positive charges, equal charges, and they would all be equally distant. This is a little bit of a geometry information, but even if you can't technically think of that, your common sense should tell you that these 3 would be balancing each other out. To be specific, that one would exert that field, this corner would exert that field, and this corner would exert that field on a positive test charge here. If these magnitudes are equal, they're 180 degrees apart, they add up to 0. Number 9 and 10 are basically the same question. They're asking you to answer very similar things. They're taken from different sessions. The field due to a negatively charged conducting sphere. Because it's negatively charged, we rule out A and B because the field lines point away. And it's not D because inside field must be 0, so this is wrong. Likewise, in number 10, again we have a negatively charged sphere. Answer is A. So that's that. Now, I also ask you to look at number 3 from the Oxford Study Guide at the end of topic 5 examples. So this is the question. We have a negatively charged sphere and the diagram shows metal sphere. First, we're asked to find the diagram to represent the electric field pattern. So let's add that in. And your lines can be any density you want, but try to show them uniform. The important thing is that they are uniform, pointing inwards, and none in the center, hence the 3 marks. Do you realize how easy 3 marks that is if you know what you're doing? The part B is the electric field strength at the surface of the sphere is determined by assuming that the sphere acts as though a point charge, 9 nanocoulombs, so this is the Q. The radius of the sphere, 4.5, 10 to the power of minus 2, that's the radius. And we're asked to find the strength at the surface of the sphere. Show that it's that number. In such questions, you make the calculation which gives you this. So this is going to be your answer. Your job, the point of the question is to show that calculation. So how do we calculate electric field? What do we know? We know electric force, K, Q1, Q2 over R squared. We also know E equals F over Q. Now bringing these together, if you divide, see if you want to find E equals F divided by Q, if you divide that by Q, this is what you're going to get. And this actually gives the electric field strength R distance from a charge Q1. And the question tells us to model the charge Q concentrated at the center, like at that point, just like we would do for a mass. And the surface would obviously be r distance away, given here. So we're looking for the electric field strength at that location. So we can use this formula that we got by rearranging these two. So our K is 9 times 10 to the power of 9. Our charge is 9 nanocoulombs. And dividing that by 4.5, 10 power minus 2 squared, don't forget the squared, you do get 40,000. The unit given here is volt per meter. We will learn about that in the topic 10 fields discussion. For now, we can also look at what we're doing to get the unit, force unit divided by charge unit. So force unit divided by charge unit. This will be the electric field strength unit, and we can justify that. The question goes on with asking, an electron is initially at rest at the surface of the sphere. So I'll draw the picture again. There is a charge here that we have. That's our given 9 to 10 to the minus 9 coulombs. So that's the 9 nanocoulomb charge that we have at radius r. Now there's an electron here. And once it's placed at the surface of the sphere. Once it's released, well, it is a negative charge, by the way, and obviously electron is also a negative charge, so they are desperate to run away. So once we look at the question which asks, describe the path followed by the electron as it leaves the surface. Now, it's only 1 mark, so you're only expected to say a brief statement here. You can say that it's going to be repelled and move away. So that's really all detail that we would give here. Then we're asked to find the initial acceleration of the electron. I'm going to take you back to the multiple choice question that we just did. Remember what we did here in number 7? We first decided what context, what force is in this context. Electric field strength times the charge placed in the field is the force. Any force can be written as mass times acceleration. Set those equal, solve for whatever is unknown. So we're going to do the same thing. We know that acceleration, I'm not going to derive it again. I'll just write the same thing. I'm going to use little e, which is the charge on an electron. We use that symbol for elementary charge. So we have that. Now, what do we know here? Do we know the electric field? Well, yeah, we just found it in the previous question. And even if we didn't, it was given to us. Charge on the electron. You will find this in the table of constants as elementary charge, as that. And divided by mass of the electron, which is also given in the data booklet as such. So when you calculate, you get 7.2, 10 to the power of 15 meters per second square. So this would be the initial acceleration of the electron, immediate acceleration as it is released. Why do we emphasize it is the immediate initial acceleration? Because as it moves away, distance is going to increase, which means the field strength will decrease. Well, if field decreases, force decreases. If force decreases, acceleration decreases. So first I can say as it moves away, acceleration will decrease. But that doesn't mean it's going to slow down because there is still force pushing it away. So it will be speeding up with acceleration decreasing. Let's write it like that. With speeding up with decreasing acceleration would be actually the 2 marks, 2 points that you would make in this question. Thank you.